Continue straight from previous video where we calculate the effective length for exterior columns. Now in this video we're going to calculate the buckling load NC. The clause 10.4.4 has given the equation to calculate the buckling load NC. Now in our examples it says that the cross sections that we're going to use for our columns, the cross section shown in the figure, it does mean that in the example number 1 in this video series we have used this cross section which is 400 by 600, and you have this compression reinforcement, tension reinforcement. We look at that in our axial load moment interaction diagrams where we look at that example. So we're going to use the same cross sections here that is given in our examples. So I did draw that one. So if I want to calculate this D0, that would be from the top fiber to the tensile steel would be 600, take away 74 gives me 526 millimeters from our cross section dimensions. Now after finding that cross sections dimensions in the figures, in the example figures, we have N star. I will show you that N star. We have given you the N star value is 200 kilonewton, that is in the red color. So 200 kilonewton, 200 kilonewton, 200 kilonewton for all interior columns. For exterior columns we have 1100 kilonewton. So in the figures for N star, we are going to work on the column buckling load for the, let's say, interior column first. So 200 kilonewtons is the axial load here, 200 kilonewtons coming here, and the moment is 360. Moment is 360 kilonewtons for these interior columns, that are N star and M stars that I written here. Now reinforcement ratio should be less than minimum value of rho minimum. Where is coming from? I'm just going to use these figures. That's the chart here. So in this chart, if I have a 2000s, so if I have a 2000s here and 360, so 360 is before 400. So if I draw the line here, I would get it here. So if I just draw the line here, 360 and 2000s, I will get this load is 2000s, moment is this one. I will get less than the reinforcement ratio less than 0.0001. That is the less than the minimum reinforcement requirement of AS3600. So in that case, we take the reinforcement ratio 0.001. We can't go below 0.0. We need to have at least reinforcement ratio of 0.001. So these assumptions that we're going to take 0.01, we're going to check later in the design process. If it is required the modifications, we're going to make a modification. But at this stage, we're going to take the reinforcement ratio 0.001 based on our load and moment demand. Now in that case, if I take 0.001 and this 2000s, if I draw the line here, I will get moment about 495 kilonewton meters. Okay, so I take the reinforcement ratio 2000 is given in our figures. I can show you again here. That is the 2000 kilonewtons is given here for all interior columns. So that is 2000 kilonewtons. For 2000 kilonewton reinforcement ratio 0.01, that's we assume. So for that case, if I draw the line here, I will get this 460 kilonewtons. So that is the 495 kilonewtons. That is given here, approximately 490 kilonewtons. Now moment at C. This is the vocabulary of the standard. So capacity factor MC equal to this 490 kilonewtons meters. So for interior columns, all these columns that you are seeing, interior columns, for all these interior columns, interior column 1, 2, 3, 4, all these interior columns, we're going to find this capacity, we're going to find this buckling load. Buckling load equation is given in this clause 10.4.4, that is written here. Now pi square for effective length of the interior columns, that effective length of the interior columns we calculated in the previous steps. I can show it to you here. Effective length for the interior columns we calculated in the last video, which is 66336 millimeters. So that is the 6636 square. 182 D0 we just found in this video. D0 was 526 millimeters. So that is 526 times by capacity 495 times by 10 to the power 6 over 1 plus beta D. Beta D given in our examples was 0.7. So that is 0.7. simplify, give me this newtons, divide by thousands, gives me this buckling load for interior columns, right? So that's buckling load for interior columns for these 4 columns. Now if I want to calculate the same procedures, exactly the same procedures for buckling load for the exterior columns. Okay, so exterior columns has exactly the same, only the difference is your effective length. You have exactly the same, only difference is the effective length. Now effective length for exterior columns we calculated, let me show you that effective length for exterior columns we calculated 5640 millimeter square. So exactly the same equations that you see here, 58640 182 d0 we calculated in this video. I can show it to you here. d0 was 526 millimeter. 5 mc, the capacity that moment capacity that we just look at, that 495 kilonewton meters times 10 to the power 6, because we convert into Newton millimeters. Please note we are working in the Newton millimeters, so therefore I convert into Newton millimeters. 1 plus 0.7. 0.7 is coming from our examples where we take the 0.7, gives me these newtons, and divide by thousands gives me the kilonewtons. Okay, so that is for buckling load for the exterior column. So in this video we look at the buckling column for these 4 columns and interior columns, and buckling load for exterior columns. In the next video we are going to calculate the moment magnifier for columns 2, 3s. Okay, thank you.